Perfect. Perfect. So we are going to study today hydrogen and its compound. Yeah. So the very first question that is that I can ask here is that why we are studying hydrogen separately, right? We will study alkali metal in a group. That means group one, then group two, then boron family, then carbon. So whole thing we are studying at a time. We are not separating an element and discussing like this. Then why we are studying hydrogen separately under the separate chapter? And the reason is, if you go through the configuration of hydrogen, the configuration of hydrogen is 1s1. If you look at the electronegativity, can you tell me what's the electronegativity of hydrogen quickly?
2.1.
2.1.
2.1 approximately on Pauling scale, right? Valency, obviously 1, sir. Okay, in nature, in which way does this hydrogen exist? At room temperature, even at higher temperature also, unless it is going to dissociate, you will get H2 gas, exist as H2 gas. Right? All right. Now let's look at its similarity. Means it was expected to be in the group 1, right? Because the outermost configuration suggests that it is having one. So in the periodic table, which we used to generally form, there you would have seen that quite often it is denoted over here. And in the modern periodic table, you would have seen that it is also kept at the head of this, means the halogen, fluorine, chlorine, bromine, iodine. So this abnormal behavior of hydrogen, because of that, we are able to place at both the places. So definitely there is similarity of hydrogen with group 1 and group 2. So what is the similarity with group 1 metals, right? So let's look at the alkali metals. So lithium, sodium, potassium, rubidium and cesium, and obviously francium is there. You can see they are all metal, they exist as solid. All metal exist as solid. This is not the similarity, this is dissimilarity. Metal, all are metal and exist in solid. So what is common point? Just the configuration. Configuration is NS1. They're also monovalent like them, right? Whereas H2 is a non-metal, my dear. Now let's look at the other thing like fluorine, chlorine, bromine. What is the property associated with that? Fluorine, chlorine, bromine, iodine, astatine. You can see that this exists as F2 in nature, F2 gas. This exists as Cl2 gas. Bromine, you know, is a liquid, I2 is a solid, and this is radioactive. These two are radioactive. So you can see that similarity of hydrogen with this alkali metal is related to its configuration. That of the fluorine, chlorine, bromine and iodine is related with its diatomic existence and non-metallic nature, molecular nature. So yes, it has similarity with the alkali metal as well as with the halogens. These are halogens. So what you have to write? Hydrogen shows similarity with both group 1, which is known as alkali metal, and group 17, which is known as halogens. Right? Hydrogen shows similarity with both group 1 and group 17. What are the similarity? You can understand now that just like them, it is having diatomic form and gaseous existence, non-metal, high electronegativity, and with them it is just the outermost configuration. Okay, fine. So can we have some other examples of the way that it is going to show similarity? So you know that sodium alkali metal form compound with halogen. With halogen forms ionic compound, right? Like NaF, NaCl, KCl, dot dot dot. Similarly, alkali metal form compound with hydrogen. What are those examples? NaH, lithium hydride, potassium hydride. These are ionic compound. Really interesting, guys. Here hydrogen is in -1 state. So if you are going to dissolve in water, you will get H minus, which will not be stable in water. So you will get at the end hydrogen gas from it. Right? So I mean to say, note, very, very important. When you are dissolving NaCl in water, solid, you will get Na plus surrounded by water, which I am writing as aqueous. Now onwards, this word aqueous means that sodium ion surrounded with the layers of the water. Similarly, Cl minus aqueous. But you can't expect that NaH or any ionic hydride in water, obviously you will get Na plus aqueous, but H minus aqueous you will not get. H minus is so intense, my dear, that it will take hydrogen from here and you are going to get OH minus. Aqueous along with hydrogen gas. Very, very important. Please mark it. So how we are getting? You can write a hint over here that this H minus is taking partial positive now. It is taking this hydrogen out. It is making H2 from here like this. So that's how we have got the whole. Right? The way alkali metal form compound with halogen, NaF, NaCl, these are ionic. Hydrogen also forms compound with halogen. And what are those? HF, HCl, HBr. They are forming, that is similarity, but the problem here is all are gas. Its boiling point is 20, but at 25 all are gas. So similarity is that it forms compound with halogen, but the dissimilarity is they are gases. Whereas the ionic compound formed by those sodium, potassium, rubidium, cesium are. So that is the reason we are trying to study the property of hydrogen separately. And that's why this chapter is. Obviously, this will be the smallest in terms of the content.
Sir,
In
came
terms
to
of the,
the points.
yeah. I hope all of you are making the notes. Right. So now we have understood the similarity of hydrogen with alkali metal and alkaline earth metal. Now let's talk about more about hydrogen. So probably this is the element where we will be studying its all the isotopes existing in the nature and their application as well, right? So let's talk about now the isotopes. We are not going to study the isotope of everything, right? Don't worry that we'll not discuss about the isotope of iron, all the isotopes of iron. But here we are supposed to discuss. So the next topic is isotopes of hydrogen. So how many different isotopes? What is isotope? As you already know that isotope means atoms having same atomic number but different mass number. Species, atomic species, same proton means atomic number, but different mass number. If you are saying mass number is different, means you are saying basically neutron number is different. Number of neutron. Right? So what are the isotopes of the hydrogen? So we have, you might be aware, in lower class also we have studied this. Hydrogen, normal hydrogen, 1H1, which is known as protium, simply represented as H. Second one is 1H2 is nothing but deuterium, simply represented as D. See, just for hydrogen, we are representing these symbols like this, HDT. Third one is 1H3, represented as, named as tritium, capital T, represented as capital T. Out of these three isotopes, if you'll talk about this third one is radioactive. So radioactive. 1H3 is radioactive species. And if you talk about the radioactive species, then we have to talk about many things associated with it. So what are the radioactive species? Species which spontaneously emit alpha, beta, and as a consequence of that, gamma radiation. There are many other things also like K captures emission of X-ray. But these three things are known from the ancient time. So alpha, beta, and gamma radiation. So now we are really interested. So what is the nature of this? Is it going to emit alpha? Is it going to emit beta? If it is going to emit alpha or beta, then what will be the new nucleus that is formed? So my dear, it is a beta emitter. Half-life, anyone? 12.33 years. So what is the meaning of this half-life? What's the meaning of this half-life? Anyone? What do you understand by the term half-life? So half-life is
Yep.
associated because it is unstable, na? So the tritium or 1H3 or tritium is going to convert into helium after emission of the beta, and the representation of this beta, you can represent it like this, -10, or you can represent like this, E -10. It is identical. I mean, you can call this as electron as well, right? So some people call it as beta negative, but as per the modern nomenclature, beta means beta negative, and the beta positive
Sir,
is known as positron, right? So
there will He2 once.
which one?
Yes, sir. Helium.
Helium will two.
Two?
Helium
No, no, no,
2.
not one. Sorry, this is three. Mass number will be intact, no? This will be three, right? So you can understand. T half is 12.33 years.
Sir, helium has four.
Relax. Just the way hydrogen is having isotope, even helium have isotope. So most abundant one is that 4, but that is not the only isotope, right? Every atom have isotope. So many different. Proton is same, but neutrons are different, right? So essentially what is happening, if you want to see here, what is happening over here? The nucleus, which comprise of one proton and two neutron, is actually converting into two proton and one neutron, and as a consequence of that, the neutron converts into proton, that beta is emitted to balance the charge. So in short, there is this representation, n is, and guys, there are many other particles also I'm expected to write, but I'm not writing this because that will be the subject related to nuclear physics. So I'm not writing like neutrino, antineutrino, right? All those things. So I'm just representing the chemistry aspect of this. Will not be requiring it anymore. Okay, so that you can refer through your physics, sir. All right, guys. So this is how the beta emission takes place. This is radioactive. So what is the meaning of half-life? What is the meaning of half-life? Huh?
The half-life is the time taken to decompose into half of the initial value.
Right. So basically, suppose there is presence of, say, for example, n number of nucleus, right? Suppose there is n number of nucleus. So after half-life, that is 12.33 years later, the remaining amount will be of tritium will be half of its value. Its value at t is equal to 0. Okay, half of its value which were present at t is equal to 0, or half of its initial value. That's how you can consider it. Now, so is there any utilization of this tritium? So yes, there is utility. You can use it for short dating technique. I mean, dating technique means is basically determining the age of something. Mostly it is used for dead samples, right? So you cannot tell the age of rock based on this concept, but yes, you can tell something which is died 5 years, 10 years down the line. So for those samples, you can check the age of that. So that is known as radio level dating. Okay, so you can use this tritium sample for that to check the age of particular thing which is died or the originated in decades only, I would say, not very long time, like 5,000, 10,000 years, like that. For that, we have other samples. Carbon dating is one of them, and uranium dating is another for rocks. Okay, so yes, so that's it about this protium, deuterium, and tritium. Okay, now the next question would be, sir, what do you think about their abundance? Okay, you told us. So I'm asking you guys to go through it. What is the abundance of it? But for now, I will tell you that this 1H1 form which you are looking here is, if I'm right, it is 99. But again, you have to copy it. That's why I have given you the reading as well. Copy and make a note here. So it is 99.98 if I'm right. Okay, just go and refer. So certainly it is 99.9, greater than 99.9%. So that's why whenever we write hydrogen, we are least bothered about deuterium and tritium. We are simply thinking that H2 means mass number will be 2 unit, 2 mu. The reality is it's not like that. But practically it is happening because these two are almost negligible, right? So this is 99.9, greater than that. This is less than 0.1%, you can understand, right? And this one is almost negligible, 10 to the power somewhere around 12 or 16%. I'm not very sure with this data, but yes, of the order of this, you can understand. So that abundance you have to write. So I'm leaving that part to you. Abundance. Relative abundance. Relative abundance. Okay, so this you have to fill up. All right, everyone. So now we are done with the isotopes of hydrogen. So is there any difference in the property of the isotope? Yes, we do have difference. We do have difference here between H and D. Many properties are different. Note. Tell me, what is your expectation about boiling point of H2, D2 and T2? Yes. Have some understanding in this and guess something.
T2.
T2 will be higher.
Huh?
T2.
T2 will be higher, na?
Yes.
Yes, sir.
Okay. And boiling point H2, D2 and T2. Simply based on molecular weight, right? Because you know that boiling point. I need not to write it again and again, right? BP stands for boiling point. And bond energy wise, Puli bhai, bond energy wise, what do you think?
H2.
What do you think about bond energy? So it's quite difficult to guess that, but I will tell you that the energy of bond related with the same way as the boiling point. Now, your explanation are most welcome if any one of you want to give an explanation related to this. You'll be really surprised to know that ionization energy of that goes in this order, HD and T. Come on. Your reasons are most welcome, guys. Go ahead. Hmm?
Sir, mass of tritium is more, so more protons, more attraction.
More proton? Don't say like this, yeah. Proton are expected to be same na for isotopes. Same proton.
More nucleons.
More nucleus.
So more nucleons is there. So how it is going to affect the ionization energy? If
More
I'm right,
attraction, sir.
IE is inversely proportional to atomic size.
huh?
Sir, mass defect.
IE is inversely proportional to atomic size, sir.
Proportional to atom. Where did you read
Inversely,
this?
inversely proportional, sir.
Atomic size. Okay, that is okay. Are these two atoms different? Both have the configuration 1s1. D has the configuration 1s1. T has. Did I tell you about the length problem in the
But
bond
more
length?
nucleons are there, no, sir. Then attractions will be more.
More nucleons, please understand. An electron is attracted by proton or neutron, both of them. What do you mean to say? The proton is same in the nucleus. Will it be attracted by neutron as well? You're trying to tell me. Only the neutrons are different, na?
Yes, sir.
So double think before you answer, please. It should be meaningful. One of the student very rightly quoted about mass defect. Who is it? What's the name of you? What's your name, buddy?
Charan, sir.
Sorry?
Charan, sir.
Charan. Okay. Fine, Charan. Your answer is absolutely correct. Mass defect. So I will tell you the general thing about looking at the ionization energy is, if you remember the Bohr theory derivation which we used to do in chemistry, sir might have taught you about this, where he took the nucleus to be stationary. He would have taken like that. And if it is stationary, in that case, we used to think only electron is making a revolution around the. In that case, the ionization derivation is me to the power 4 upon 8 epsilon 0 square h square into z square by n square. N square means 1 square, right? So is that the expression that you guys have studied? And all of these, if you just simply write it down, that will be 13.6 into z square. If it is ionized from, and that too for the hydrogen-like species. But the problem here is, in actual case, by the conservation of momentum, the electron does not revolve around the nucleus. Rather, both of these systems revolve around their common center of mass. So even this is going to revolve like this. And this is also going to revolve like this, my dear. So effectively, this is the radius, not from the nucleus for the electronic movement. Obviously, this R1 and R2 wise, this R1 will be very, very large. Sorry, yeah, R1 means the electronic movement radius will be much larger than that. But of course, it do have effect. So now your question will be, sir, then do we have to apply the angular momentum conservation and all of these things to derive? Answer is yes, you have to. But if you want to be quick enough, then you simply replace mass by mass defect m1 m2 upon m1 plus so now by using this, basically m1 is the mass of electron. This I will write as small m, then capital M, then divided by small m plus capital M, where small m is electron and capital M is nucleus. Now if you increase the mass of the nucleus, in what way it is going to? Tell me. In what way it is going to? In what way it is going to affect this? If you increase capital M. So I think this M is replaced by this. So this whole value will increase, isn't it? Just check it out. You divide with capital M, top and bottom. So if you increase capital M, don't you think this value is going to decrease? So overall value is going to increase, yes or no? Yes or no, guys?
Yes.
So that's the reason why the ionization energy increases. The answer is yes, because of the mass number. But how it is related with that you are supposed to do. Okay? That you are supposed to do. Anyway. So ionization energy, just I gave you an idea that how it is related with boiling point H2D2. T2 bond energy is also in that way. Ionization energy is also in that way. Right. Okay. Now that's it about the isotope. Now let's look at the other property. Apart from isotope, there is a term called nuclear isomer. So let's talk about that. Let's talk about nuclear isomer. Very interesting. That topic is also really interesting, non-traditional in nature, because you haven't understood it well, right? All related to the nucleus. Thankfully, hydrogen is so small, we are able to, this topic is really small. That's why we are able to discuss all these elementary things. But in the higher topics, like for the oxygen family, will not go that deep for every atom, right? There we will be looking at the general properties only. So the nuclear isomer of hydrogen. And they are ortho and parahydrogen. What are ortho and parahydrogen? They differ in nuclear spin. They differ in primarily they differ in nuclear spin. So they are a nuclear isomer, right? Now let's understand the meaning of that. Let's understand the meaning of that. Here you will come to know about a entirely new thing, that there is a spin of the nucleons as well. My dear, again I am using the word, there is spin of the nucleons as well. What are nucleons, guys? What are nucleons? Nucleons means species lying inside the nucleus. So mostly it is neutron and proton only, right? Neutron and proton. So when a hydrogen atom, this is the nucleus, combines with another hydrogen atom, the moment they are combining, as per the valence bond theory, we know that they will be combining in such a way that pairing of unpaired electron will take place. Yes or no? Here also I'm going to do in the same way. Yes or no?
Yes, sir.
Pairing. Done. Nucleus and nucleus. Right now, I'm talking about hydrogen, the protium one, right? Ortho and parahydrogen, I'm discussing about that, which is most abundant one, right? So, one particular form here I'm writing is ortho form, and the other side I'm writing is para form. I'll show you the difference. So, what is the difference? So, till now, in atomic structure, you know that there is electronic spin. So, net electronic spin, net electronic spin, can you tell me what will be the value of that? So, sir, plus half and minus half, value is 0. Here also, the net electronic spin is 0. 0. But my dear, when I'm talking about orthohydrogen and parahydrogen, the way electron have spin, the same way even nucleon, that means proton and neutron have spin. The way electron is having magnetic moment, in that way even nucleon have nuclear magnetic moment. So you need to understand this, that even proton and neutron have spin, plus half and minus half. So what happens in orthohydrogen, because I'm talking about just the hydrogen H1H1, so only one proton is there, so it is considered and said to be when they have the same spin, means plus half and plus half, nuclear spin, plus half and plus half the other, H2, nuclear spin of H2. I'm telling you which H2, orthohydrogen, orthohydrogen, so which is coming out to be plus half and plus half, which is 1. Here nuclear spin plus half and minus half. This is the symbol I am trying to tell you. Please understand, spin notation is there for. So what is the new point that you learned? Note, like electron, even proton and neutron have spin plus half minus half. So based on that argument, so that's why you look at, I use the word that they are nuclear isomer. Which isomer are they? Nuclear isomer. Now many questions will arise in this. Sir, suppose if we are able to get those isomers, if we are able to isolate those isomers, so will there be any difference in property the way we have seen for the isotopes? Will there be any difference in property? So answer is yes, there is difference in the property. Excuse me guys for this. There is difference in the property of ortho and parahydrogen. What are those? the melting point, specific heat capacity, vapor pressure, right? Conductivity, all of these are different for these two isomers. So I will tell you that which portion is higher for which one. But let's talk about their percentage in a sample of hydrogen. Suppose if I anyhow collected the sample of hydrogen of, say for example, 1 mole, then out of that 1 mole or out of 100 such species, 100 such H2 species, how many will be there in ortho and how many will be para? So will it depend on temperature? Answer is yes. They also depends on, the resistance also depends on temperature. So very, very important. This was the point number 1, nuclear spin. Number 2, difference is at 0 Kelvin, guys, at 0 Kelvin, right? Percentage of ortho in the nature will be 0. At 0 Kelvin, obviously the percentage of para will be 100%. This is also really interesting. If you reach close to 0, the ortho form will decrease and ultimately attain 0. You know, at room temperature, at 25 degrees centigrade, which is room temperature, percentage ortho, any guess how much it will be? 75%. So at 25 degree, percentage para will be naturally 25%. Right? So let's look at the other property as well, and you write it separately. Note, ortho have higher values of melting point, boiling point, specific heat, vapor pressure, but para have higher conductivity. As I'm telling you, these are the crude information, guys. So these are the things which you cannot apply logic right now at this instant. Okay. So for them to settle in your mind, it is really, really important for you to go for revision cycle, not for one, for many times. So that is how these two isomers, the nuclear isomers are, right? So ortho and para hydrogen differ in electronic spin? No, sir. Nuclear spin? Yes. Ortho is having what value? So plus half plus plus half will be having nuclear spin as 1. The nuclear spin on the other side, para hydrogen will be. So don't you think that the way we used to say that paramagnetic means having unpaired electron. So electron here is paired, but the nucleus is also paired here. So it is contrary to the traditional para term like paramagnetic. It is not like that. So para 1 is having 0, both of these 0. Nuclear spin and electronic spin, both of them are 0. Whereas the ortho 1, electronic spin in any case will be 0. The nuclear is non-zero, and that is 1 plus half of 1 and the plus half the other. Right? And the other properties, as I told you, at 0 Kelvin, percentage ortho will be 0. You can remember as ortho is having O, which is referring 0. So you can just correlate like that. So you have to apply your logic to remember these facts. It's up to you guys. So this is ortho and para hydrogen. So fine. So we studied about the different isotopes and associated properties. nuclear, isomer, ortho and para. Now we'll be studying about different forms of the hydrogen.
Someone's could scroll up. Sir, once could scroll up.
Right. So what is it all about? What do I mean by different forms of hydrogen? So this is basically based on the hydrogen obtained from the different source. Okay. So hydrogen obtained from different sources have different reactivity. So that's why this topic is basically different forms of hydrogen. Basically, I'm trying to tell you the different sources with which it is obtained and their reactivity. So let's first talk about ordinary hydrogen. Number one is ordinary hydrogen. Then thereafter, nascent hydrogen, I will tell you. Nascent hydrogen, which is also known by the name newly born hydrogen. Then I will tell you about atomic hydrogen. Then I will tell you about adsorbed hydrogen, occluded, occluded, O-double-C-L-U. Please mind my spelling, guys. It might be wrong. So occluded, O-double-C-L-U-D-E-D, occluded hydrogen. So simply write adsorbed. It is okay, right? And other things are also there, but I would like to restrict till here only. So ordinary, nascent, atomic, and adsorbed hydrogen. So let's talk about first atomic. Sorry, ordinary hydrogen. Tell me, what do you understand by the word? The word itself tells ordinary. So what is ordinary hydrogen? Any hydrogen which is obtained and stored for long time. Hydrogen which is obtained and stored for long time. Hydrogen obtained from any source, but kept for long time. Becomes ordinary hydrogen. Like if you are obtaining hydrogen directly from the air, that is, and if you are storing it, that is also a normal hydrogen. Okay, let's talk about nascent one and we'll look at the difference between these two. Okay. So what is nascent hydrogen? Hmm? Obtained at the time of reaction, during the course of reaction. Right? Now, what is the difference? This is also said to be newly born hydrogen. This can also be said term as newly born hydrogen. Right? So now what is the difference between them? So my dear, suppose you have stored one hydrogen sample and you have KMnO4 and H2SO4. So if you are passing ordinary hydrogen, there will not be any color change. You know KMnO4 is which color? Which color do you think that KMnO4 is?
Purple.
And no color change. Observed. Right? So the color of KMnO4 will be changed the moment you are trying to get the value H2SO4. This reaction you are doing, it is providing you ZnSO4 plus hydrogen. So we write like this, right? This is hydrogen. At the end, it will become H2, but we are just representing it like this. So this hydrogen, this is nascent hydrogen, right? This is dilute. Very important, very, very important. So what happens? Suppose if you have the same thing, like you are having H2SO4 and KMnO4. Simply you are putting zinc into it. So basically, this reaction of zinc with this is producing the nascent hydrogen, right? If you are able to pass that, what will happen? That hydrogen is going to reduce KMnO4. Color change. So KMnO4 is going to react with these two. Sorry, it is going to react with the nascent hydrogen, and that is going to reduce Mn plus 2, MnSO4 plus 2. It was purple, and this is colorless, almost colorless, although very weak color is there, but colorless. We will not use the word colorless. You can see that. That is the thing. So it is a powerful reducing agent. So it is reducing that. So you can see that how the nascent hydrogen is differing in terms of property. Third thing I would like to write here is, so you can make a comment over here that ordinary hydrogen does not reduce KMnO4, whereas the nascent hydrogen reduces KMnO4. Understood my point? Understood now? Fine. So let's talk about the next hydrogen. What was that? Did I tell at the beginning? About atomic hydrogen. As the name suggests that right? So hydrogen, it's hydrogen, atomic hydrogen is obtained. Suppose you are able to break the bond of hydrogen, right? So how will you break the hydrogen bond? So if you are providing spark, electric spark, so you are going to basically break this into H plus H. So this one is atomic hydrogen. They are highly reactive. Atomic hydrogen is highly reactive. And they recombine immediately. Guys, please excuse me for my spelling, okay? I really don't know. Immediate. Idle. Is it idle? Okay. Immediately. Please write it down, okay? IMM. E. It should be E. No, it is okay. Immediately. All right. TELY. All right. So immediately they recombine immediately and evolve enormous amount of heat. Enormous amount of heat. Now you can see that that heat could be used as per the practical requirement that we have. So this is used in welding torches. That much heat is required there, right? So basically H plus H, H2, excessive heat. You can understand this value. This value delta H is approximately 104 kilocalorie per mole. It's not in kilojoule, guys, okay? Kilocalorie. So means more than 400 kilojoule will be evolved, right? So this can be used in welding torch. Used in welding torch. This whole mechanism is used in welding torch. Welding torches. Right? So then what is atomic hydrogen? Obviously, hydrogen obtained in atomic form. Right? You supply the energy. Mostly electric spark, as I told you, is the best thing that you can do. And the last information I would like to give on what is the adsorbed. Look at the word, it's not absorbed, it is adsorbed. So what is adsorbed hydrogen? The name suggests that, like you'd have seen in many hydrogenation case, like if you are hydrogenating this, you'd have seen these examples, right? Nickel, palladium, platinum, hydrogen, nickel, hydrogen, platinum, hydrogen. They are simply hydrogenating it. So what happens? We are not providing the source of hydrogen externally. It is first we are trying to get these hydrogen into the crystal of these, and thereafter we are doing some process with it. So I will tell you, hydrogen which are adsorbed in the crystal of the metal. Hydrogen which are adsorbed in the crystal of solid. So mostly metal ही रहता है वो, in the crystal of metal, right? So how does it happen? So basically, if you are having hydrogen and there is a metal crystal, right? Suppose I'm taking a metal crystal. I'm trying to take a metal crystal. I'm trying to form. Suppose I'm taking a very simple crystal. Suppose this is nickel, and if H2, 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 and if I heated this, so what will happen, that these hydrogens, because of heating, the thermal expansion occurs. So during vibration, you'll get space where hydrogen can enter. So hydrogen basically enters in the atomic form. Yeah. So I should reuse the different color over here. It will not be very uniform in nature, guys. It will not be uniform, I'm telling you. That's why I don't need to make any pattern out of it. So this is this hydrogen I was talking about. Right. So one of the molecule I have shown you like that. So this is adsorbed. Present in the voids. Present in the voids. Voids means open space, empty space of the crystal. Right? Useful in reduction. So this is the reduction I have shown uses. So that is it, my dear. That's it for today's class. Tomorrow, what I am going to teach you is preparation. But as I told you, this requires multiple reading. So I will give you a reading assignment that you have to read the NCERT, the whole process by which we used to produce hydrogen. Right? That is one thing that you have to do. Different types of hydride, what are there, that you have to do. So for tomorrow, first 6 pages you have to read. 6 pages of NCERT. Right? So this one you have to read, and once you are done with that reading, not tomorrow, in fact today only, whenever you are getting time, and once you are done with that, thereafter you can try the question which is given on day 1. That is also posted there, right? So you go ahead, and this is it. Keep revising. Inorganic, again I'm telling you, requires a different approach, and you guys are good. So I hope you can cover by yourself, right? So that's it, everybody. That's it for the class. Thank you so much for attending the class.